All right, so let's do a review question or a review problem set on regression. And you can see that I have three windows open. I have the problem set, and I created a cheat sheet with all the formulas that we have derived. And the main objective of this problem set is just to review again the concepts and the accuracy of the formula and their interpretation. So we have some data. We have like 1, 2, 3, 4, 5, 6 data points, and we need to do a regression analysis on it. So the first thing we need to do is draw the scatter plot, so that should be helpful. So let's, okay, first one, 0 and 4. So we have a dot here. Then 1 and 7, that would be here. Then 1 and 5, that would be here. Then 3 and 11, that would be here. Then 3 and 9 would be here, and 4 and 12, that would be here. Okay, so if we were supposed to draw now a line of best fit, we can obviously already tell that this scatter plot has a positive linear relationship, and if we were supposed to draw a line of best fit, even without going through the math, we probably will see that this curve, the line of best fit, starts at 4 and has a slope of 2. So the predicted trend line, just before going into the math, is y hat equals, the intercept is 4 plus, and then the slope is 2, so plus 2 times xi. So that is the trend line. But now let's verify that with the formulas that we derived. And the first question is, what is the intercept? Okay, it's probably 4, but let's just create a column for the xi and the yi, and let's make it nicely, and let's subscript the I. Let's go to 4, let's subscript it. Okay, so we have the x value 0, 1, 1, 3, 3, 4, and for the y's it was the 4, the 7, 5, 11, 7, 5, 11, 9, and 12. And then what we need, like a bit here, what we need is definitely the mean of each group. So let's highlight, this is our data set here. Let's highlight it maybe in light orange. And okay, so now the mean of each group is equal to, probably can do that in our head, so 0, 1, 2, 5, 8, 12. 12 divided by 6 should be 2, average. It is 2. And by the way, every regression line, linear regression line, goes through the mean of all the variables. So we already have seen the mean is 2. So that means, because we know that a characteristic of a regression line is that it goes through all the means, the average of the y must be 8. So let's just see if that is right, and let's copy the formula to the right, and we see that this is indeed correct. Okay, so now in order to calculate the intercept, which is probably 4, we first need the slope coefficient, and again the slope coefficient b, which we probably find is 2, is given by the sum of, well, it is the covariance over x and y over the variance of x, but the covariance is written as xi minus x bar times yi minus y bar, which is the mean. So that's the product of the deviations from the respective means of x and y. And then we divide by the sum of the xi minus x bar squared. So technically I still would have to divide each one by 5 and minus 1, but that will cancel out, so I just can focus on this one. And again, another way of writing that is the covariance of x and y over the variance of x. And so what we need now is, I need to create a new column that I call, let me copy this one, xi minus x bar, and let's subscript again the I, and also yi minus y bar, then we need also xi minus x bar squared. But I put that into parentheses, xi minus x bar squared. So then we have to subscript the I, and superscript the 2, maybe not the parentheses. Okay, so now it looks right. Okay, xi minus x bar is equal to xi minus, now we always take the mean, and I put an F4, the two dollar signs around it, and then I can copy down that formula. You can copy down with Control D. Then yi minus y bar, same thing. So we navigate to the first cell of the yi's, and then we subtract the mean. And we put again an F4 around. And we copy that down. And actually before the xi minus x bar, I think it makes more sense to have first xi minus x bar times yi minus y bar, and put again a subscript. Okay, so now it looks nice. So now we can already calculate the xi minus x bar times yi minus y bar. And here I subscript the sum sign. That also doesn't look right. So, but now. Okay, so now we multiply -2 times -4. So that's 8, and now we do the multiplication also for all the others. And center it. And now, in order to fill the denominator and the numerator, we need a sum. Okay, so the sum is equal to 8, 9, 12, 15, 16, 24. But let's double check using the formula sum. It is 24. Next we need xi minus x bar squared. So we have already xi minus x bar. So let's navigate to the first observation of xi minus x bar and square it. So that's a 4. And let's also sum that up. So that is 4, 5, 6, 7, 8, 12. So sum equals indeed 12. So now we have that the covariance is 24, the variance is 12, and that gives us indeed a slope of 2. Okay, so that means we can already write intercept and slope, and we know the slope is equal to the 24 divided by the 12. And now the intercept, that is, we can look to our cheat sheet, y bar minus bx bar, so that is equal to the 8 minus the slope times the mean of x, and that is indeed 4. Okay, so now we know that, yeah, this intercept is indeed 4, and the slope coefficient is 2. So now what about the standard error of the regression? And again, we have that also here in the cheat sheet. So what we now additionally need is the y hat. So let's create another column for yi hat. And to make it look nicer, let's subscript the I. So the predicted value is equal to 4, because that's the intercept, plus 2 times, I could also navigate to the intercept and to the slope, and F4 it. So plus 2 F4 times xi and copy it down, and let's maybe center it. So now we have yi hat, and then what we need is yi minus y hat squared. So yi minus yi hat, and that goes all in parentheses, and we square it. So again, the I home and the squared so now we navigate to the first yi and we subtract the y hat and we put parentheses around and square it. So the first one is a 0, and now we copy down for the other 5 observations, and then we need to sum it up. So the sum is 4. Okay, now we have to divide by n minus 2. So we have 6 observations minus 2, that gives us 4, and then we get 4 over 4, that's 1, and now we have to take the square root, so that's 1. So the standard error of the regression is equal to the square root of all the deviations of the actual y from the predicted divided by 6 minus 2. Again, we have only 4 degrees of freedom. Because degrees of freedom is always the number of observations minus the estimated parameters, and because we needed to estimate the slope and the intercept, we have to subtract 2. So the standard error is, the regression is 1. Okay, what is the sample variance of your intercept? Well, what we can do is we have here only the formula for the standard error, and the variance just would be the squared standard error. So the variance of the intercept is variance of A, and then the next question is what's the variance, and then the standard error. Okay, standard error of A, and then we have the variance of B and the standard error of B. So let's just focus on the formula now for the standard error of the intercept, and that is the sum of all the xi squared. So maybe let's create another column and call it xi squared. And then and the 2 goes up. So let's square all the xi, so that is equal to, okay, 0 squared. Then we copy down the formula and we calculate the sum. Okay, so that's 36. So now we can already see that the standard error is in the numerator, so we are looking at this formula now. So we have the square root of 36 over n times the squared deviations of xi, which is xi minus x bar. We already have that too. That's 12 times the standard error of the regression. That's the standard error. So let's just do this. Equals. Okay, so we start with square root. And in the square root, what goes into it is the sum of the xi square, the 36, divided by open parentheses, n, which is 6, we have 6 observations, times the sum of the squared deviations from the mean, which is the 12, times, so now we are done with the square root, times the standard error of the regression, which is just 1. So that's the standard error. So because that is 1, it's actually not 1, it's limited to 3 decimals, so it's 0.701. So the variance of A is simply the square root of the standard error. So let's also, so that's 0.5. So now let's do the same for the slope. So let's calculate the slope. And we go first to the standard error. That's a little bit easier. So that is equal to the standard error of the regression, which is the 1 divided by the square root of the squared deviations from the mean, and that was the 12. So let's click into the cell with the 12. And there we get a standard error of 2.89. So the variance of B must be the standard error squared. Okay, so okay, so what is the sample variance of your intercept? That is the 0.5. What is the standard error? What is the sample variance? That's 0.5. What is the standard error of your intercept? Round to 3 digits, 0.707. What is the sample variance of your slope estimate? That's the variance of B, 0.083. What is the standard error of your slope estimate? That's the 0.289. Okay, so now we conduct a t-test of significance on your estimated coefficients. And so the way it works is, what we know is that we have a sampling distribution. And actually, before we get there, how many degrees of freedom do we have? Well, the degrees of freedom is n minus 2. So the correct answer is 4. So now we conduct a two-tailed test at the significant level of, that's supposed to be alpha. Of alpha 5% on your estimated coefficients. At what absolute critical t-scores would you reject the null hypothesis? So a two-tailed test. So then the critical t for rejecting the null hypothesis would be determined by the formula t dot inverse And then, because we want to have 0.025 or 2.5 probability in each corner, we can get that critical T with the formula T dot inverse INV 0.025, 4 degrees of freedom. And now we get negative 2.8, but I will absolute it. And so now, and I'm going to add maybe limited to 3. Okay. So rounded to 3 digit, it is 2.776. So that means if we do a hypothesis test, we know that we need to look for a critical T to the left and to the right. So that's one T critical. And here we have another T critical. And it means to the right of 2.776. And to the left of negative 2.776, that is where we have our rejection zone. So these orange fields are our rejection zone. So in other words, if our estimated intercept or estimated slope coefficient is more than 2.776 standard errors away from a hypothetical mean of 0, because that's the null hypothesis, that we assume that the slope coefficient is 0, then it will fall into the rejection zone. So our critical T is 2.776, and so the correct answer is C. So, but what is your actual T-score for the intercept? So for the intercept, we have now what we call the test statistic. So the test statistic for the intercept A is, so for the intercept A, we got 4. And now we need to divide that by the standard error of A, which is 0.707. And if we do that in Excel quickly, I just call that test stat A. So the test stat A would be equal to the actual estimate divided by the standard error of this estimate, which is the 0.707. And then we get a pretty high value, which is 5.657. So that of course suggests that it falls deeply into the rejection zone, so it is very, very significant. So 5.675. 7. So that clearly falls into the rejection zone, so that would be somewhere, deep inside. And that would be our 5.657 test stat. And you see there would be barely any type 1 error left. That would be a very, very, very small type 1 error. So we make that, so this remaining probability times 2, it's very, very small. So what would you conclude when running a two-tailed test on the intercept of alpha 0.05 Well, using the appropriate scientific language, we reject the null. There are only two things you can do in statistics when it comes to hypothesis tests. You either reject the null or you fail to reject the null. That's the correct language. Well, what is the probability that you made a type 1 error in your hypothesis test of the intercept? So now we need to look at what is the probability that we get something. What's the probability to the right of 0.5657 or to the left of 5.657, but now we need to multiply that times 2 because it's a two-tailed test. So now the way to do this is we can use the command t.dist, and then I want the area to the left of 5.657, so I put a negative in front. And then Excel wants to know how many degrees of freedom do we have. We have 4. And then the question is, do we want it cumulatively, yes or no? And the answer is 1, yes. And then we still have to multiply times 2. So that means the p-value associated with A, which is the probability that we made a type 1 error, I actually cut that right into here, is 0.005. So that would be 0.5%. So yeah. So that means it is highly significant. The probability that we made a type 1 error is very, very small. Okay, so your actual t-score for the slope coefficient. So now we do the same thing for the slope coefficient. So for the slope coefficient, we again assume that we have a sampling distribution. And we still know that our critical t, that hasn't changed. So the critical t is still 2.776, negative to the left, and positive 2.776 to the right. So there we have 2.5% probability mass in each pocket. And so now our test stat for the slope coefficient is test stat for our slope B. That is the 2, the slope, we estimated 2. And now, what's the standard error for B? That's the 0.289. And that is, yeah, even more significant. So that is 6.928. So that is also deep in the rejection zone. So this suggests that our slope is very, very significant. So that also falls deeply into the rejection zone. So our test statistic is 6.928, and that is our t-test stat. So what do you conclude when running a two-tailed test on the slope coefficient? Again, we reject the null. And again, what's the probability that we made a type 1 error? That should be even less than before, so it must be less than 0.005. So we use again the formula, so p-value, but this time it is b. And that is equal to t.dist. That's the formula that we use, and then I put a minus sign in there. And then I click into the cell where we have the 6.928, our test statistic, comma, 4 degrees of freedom, comma 1 for cumulative. Don't forget to multiply times 2. And now we get 0.002. So that is less than, the probability of having made a type 1 error is less than 1%. Okay, so that means our regression result, they are highly significant. And so now let's turn next to the ANOVA table. And when it comes to the ANOVA table, we first look at the explained sum of squares. And for this I go back to our graph. And let's do an ANOVA table here. So we are done with this. And I'll try to sketch here an ANOVA table. Okay, so here we have the explained sum of square, which is what does the regression explain. Then we have the residual sum of squares, and we have the total sum of squares. Okay. But yeah, let's just write it like the regression. What does the regression explain? How much residuals do we have? And then we have here the sum of squares. And then we have here also the total. So when it comes to what explains the regression, so that is all relative to the mean of y. So let me put here a horizontal line at y bar. So now, what is the explained sum of squares? Well, the trend line at the first dot would explain a 1, 2, 3, 4 unit deviation away from the mean. So the mean is 8, but the trend line suggests it should be 4. So that is a 4 unit deviation from the mean. So the explained sum of squared, and again the formula is the mean minus the predicted squared. So the first term is 4 squared, which is 16. So then, if we take a look at those two dots, so we have twice the 1. So we are twice predicting a 1, 2 unit distance away from the mean. So that is twice a 4. So 4, 4. Then we have those two dots above the 3, but the trend line again predicts a 2 unit deviation above the mean. So we have again a 4 and a 4, 2 squared, 2 squared. And the last one is again a 1, 2, 3, 4 unit deviation from the mean. So that's a 16. So now we can sum that up. That is 16, 20, 24, 28, 32, 38, 48. So the explained sum of squared of the regression is 48. So what about the residuals? So the residuals, so we're looking at the residuals. Well, the first one, the first observation doesn't have a residual, so that's 0. But then the two observations above the x of 1, they have each a residual of either positive or negative 1, but squared, that is twice of 1. Then the two observations above the 3, they also have a residual of 1 each, 1, 1. And the last observation, the observation above the 4, has again a 0 residual. So the residual sum of squares is very low, which is a good sign. So that is only 4. So the total sum of squares is 52. Then the next thing is, how many degrees of freedom do we have? And for the regression, the degrees of freedom is k minus 1. So because we have two coefficients that we estimated, we have 1 degree of freedom. For the residuals, because we have 1, 2, 3, 4, 5, 6 observations, we have to subtract the number of coefficients, so we get 4. And then we calculate the mean sum of squares. And then that means each regression coefficient on average, or each freely varying coefficient explains a lot for the 8 on average. So 48 over 1, that's 48. And the average residual of the freely varying observations, it's only 1. So that means our F statistic is 48. Over 1. Okay, so now let's go back to the questions. The explained sum of squares of the regression, we just said that's 48. The residual sum of squares was very low, 4. The total sum of squares was 52. So now what is the R squared? Okay, so the R squared is the explained sum of squared over the total sum of squared. That is correct. So that is definitely, so we know this is correct. And we had the explained sum of squared was 48. The total sum of squares was 52. Well, maybe this can be shortened. That's the same as 24 over 26. Or it's also the same as 12 over 13. So, well, this is correct, and if we use our calculator and we just quickly calculate the R squared, or R square, it is 12 over 13, which is indeed 0.923. So this is a very, very high R squared. So all of the above are correct. Then the next question is, what is the F ratio of your model? And we said, well, this is 48. How many degrees of freedom do you have in the numerator? And that was the number of coefficients. So that is related to the regression. We have two coefficients, minus 1. So k minus 1 is 1. How many degrees of freedom do you have in the denominator? That was n minus the number of coefficients. So that is 4. And what is the mean sum squares of the regression? So that's that was the 48. The mean squares of the residuals, we said this was 1. So if we conduct the hypothesis test on the overall significance of your model and choose an alpha of 0.01, you can either look up a t-value in an F table. No, we will not do that. We use the Excel command. Then what is the critical value? So I call that F critical. So when would we reject? So for this we use the command f.inf right-tailed. So that command tells us we want to have in the right tail 0.01 probability mass. Then Excel wants to know how many degrees of freedom do we have in the numerator. That's the first one. Degrees of freedom 1 is the numerator. 1, comma, degrees of freedom denominator 4. So this is a very high critical value. So that's 21.2 if we round it. Well, so, but what do we conclude when running an F-test on the entire model using alpha, using 1? Well, our test statistic, our F-test was 48. Well, that's clearly in the rejection zone, very deep in the rejection zone. So we reject the null. Okay, so what is the probability that we actually made a type 1 error? So that is the p-value of the F-test. So that means we want to know what is the area to the right of an F-test of 48. So what's the area to the right? So that is equal to F dist right-tailed, and then the degrees of F, we have to use 48, and then again degrees of freedom 1 and 4. And then we get again a probability of 0.002. Or I'm going to pull up, okay, so rounded it is 0.002. So, but for a regression with only one slope coefficient, which statement is true? The p-value for the slope coefficient is the same as the p-value for the F-test. Yeah, that is true. And we can see that again here. So here the p-value is 0.00228. If we go to the p-value of the slope coefficient and I add more decimals, you see it's the same. And so we always add more. You see, and that shows you that all those distributions, they are all interrelated. Okay, and of course B, C, and D, they are wrong. The p-value for the intercept is the same as the p-value. No, the t-score, no, the t-scores are different. So it is 28. Okay, so that was just again a review. Of course, the point was here to say that things can be calculated. I wanted to give you a slight overview of how those formulas are calculated. I hope it gives you a little bit of sense of the underlying math. But of course, more importantly, we just want to use a statistical software program and just run the regression. So if we now just take a look at our model, of course what we will do is we just go to data analysis, and then we can run a regression. So if we go to regression, where is it? Here. Then okay. So our data has labels X, Y, and YI. So the Y range, we highlight all the YIs, including the column header YI. Input range, same thing, we highlight all the XIs, including the column header. So that means we check that we have labels. And then all we need now is just the output, but I want to show it next to our calculations. That's it. and now we get the regression output. And let's just quickly limit everything to 3 decimal points. So you can see, first thing we know is the R squared is 0.923, which is what we got here as well. The standard error of the regression is 1, which we calculated here as well. Then the degrees of freedom, the ANOVA table. So, and here, okay, we can see that our standard errors are the same. Let's fit that here onto content. So the coefficients 4 and 2, that's what we got as well. Then the standard error 0.707. And the standard error for B, the 2.89. The T-stat 5.657. And the T-stat 6.928. So now you all should know where those numbers come from, how to calculate them, and also the p-values, the 0.05 and the p-value for B 0.002. And the F statistic, so you should have at this point a pretty good understanding of how to interpret the coefficients and the hypothesis test that you need to do in order to evaluate your model. And yeah, so that's pretty much it. And yeah, I hope that this was useful, and you should be now prepared at least to conduct some very simple regressions, including multivariate regressions, because when it comes to the interpretation of the coefficients, nothing really changes. All right, so that's it on regression analysis, and yeah, I hope you found it useful.